Chapter 10 lecture. Chapter 10 is on liquids and solids, and we're going to only cover sections 10.1 through 10.3. We're going to look at the molecular forces that exist between molecules in liquids and solids, and we're going to use that to explain the macroscopic behavior, the bulk behavior that we see in liquids and solids. Let's take a look at, first of all, at the forces between liquids and solids, between molecules in liquids and solids. Those types of forces are called intermolecular forces. We are going to use this term a lot in this chapter, so get used to the term, and you're going to think of a lot of these problems, which are mostly conceptual. There are no calculation problems for this chapter. You're going to think of them in terms of the intermolecular forces that exist between the molecules. What are intermolecular forces? The definition of intermolecular forces is that it's those types of forces that exist between the molecules of a substance, not within one molecule, that is intramolecular forces within the same molecule. For example, if I have H2O, what is the force between hydrogen and oxygen in that H2O molecule? But intermolecular forces are forces between water molecules themselves. So one H2O molecule to another H2O molecule. That's what inter stands for, between molecules. Now these can be the same type of molecule, or they can be different types of molecules. I can have a mixture of two liquids, for example, and the forces between those two liquid molecules, there be two different types, let's say ethanol and water. The forces between water molecules and the forces between ethanol molecules, alcohol, whatever the alcohol is, will be intermolecular forces. So between molecules, not within the same molecule. Now we observe something interesting about intermolecular forces. Let's start with a solid. In the solid, intermolecular forces are very strong, and we know this, the solid molecules are really close to each other, and therefore the interaction between molecules is very strong. Now what happens if I increase the kinetic energy in terms of temperature of the solid? As I increase the temperature, which translates into kinetic energy, these molecules start to gain enough energy that they can overcome those forces that hold them there. If they overcome those forces, the solid starts to break down, starts to melt, and it turns into a liquid. Where the intermolecular forces are still there, but they're not as strong as they are in a solid, which is a crystalline solid. And we can see that because the liquid doesn't hold its shape very well. It just takes the shape of the container that it's in, whereas the solid has a very rigid structure that comes because the intermolecular forces in a solid are much stronger than they are in a liquid. Now what happens if I keep increasing the temperature and therefore the kinetic energy? We all know from experience, once again, that the liquid molecules will move even faster. As they move faster, they're going to expand, they're going to move away from each other into the gas molecules. They become gas. So the liquid converts to a gaseous state. These molecules have very, very high kinetic energies, and therefore they do not have, they're very far apart, So the intermolecular forces are not very strong. They're very weak. We've mentioned a little bit about the strong nuclear force that varied with distance back in when we talked about chapter 20. But the same idea works for intermolecular forces. The farther the distance between molecules, the weaker the intermolecular forces are. So if you were given a solid, a liquid, and a gas, and were asked which one of these has the strongest or the highest intermolecular forces, you would say, well, my solid does, because the distance between the molecules is very small, and therefore the intermolecular forces are larger. The relationship between intermolecular forces and kinetic energy is an indirect relationship. So as I increase the kinetic energy or the temperature of the system, the intermolecular forces decrease. You can see the arrow this way, so increases from gas to solid, but the kinetic energy increases in the opposite direction, from solid to gas. So these two terms are inversely related. If I increase the intermolecular forces, that means that the kinetic energy is less, because the attraction between molecules is stronger, and because the attraction is stronger, these molecules are not moving so fast now, because think of them as sticky molecules. As they're interacting more with each other, they're sticking to each other, so they cannot move that much, and therefore the kinetic energy decreases. So keep that in mind. Intermolecular forces vary inversely with the kinetic energy. What are the intermolecular forces? We have a collective term that we use for intermolecular forces, and this is van der Waals forces. They're named after the guy who first studied them, so they're called van der Waals, but it's the same thing. So if you hear intermolecular forces or van der Waals, they're the same. They describe the same phenomenon. But for this class, we will talk about three main forces. The first one, London dispersion forces. The second is dipole-dipole interactions. And the last one is hydrogen bonding. The way I have listed them here, they're in order of increasing strength. The weakest are London dispersion forces. Then come dipole-dipole interactions. Then come hydrogen bonding. A molecule or a specific compound, so molecules of a specific compound, may have all three of these types of forces, or they may have only one, or they may have only two. The more types they have, the stronger the intermolecular force or the van der Waals forces in general, because they're additive. So if a molecule has some London dispersion forces and dipole-dipole interactions, but the other type of molecule only has London dispersion forces, then the one who has two types of forces will have the strongest van der Waals or intermolecular forces, because they're additive. Let's then talk about each one of these in turn. London dispersion forces. London dispersion forces are the weakest intermolecular forces. They're a result, so they come about from random fluctuations of electron density within an atom or a nucleus. They're very weak. They're present in all neutral systems or in all nonpolar systems. They depend on the size and shape of the molecule, and we'll talk about it in a little bit. But these are the characteristics of London dispersion forces. Every molecule will have at least London dispersion forces. But typically we only see London dispersion forces in nonpolar environment. Other a polar molecule will have London dispersion forces and other intermolecular forces, but typically nonpolar molecules will only have London dispersion forces and nothing else because they're nonpolar. So how do we understand London dispersion forces? Well, if this is my atom, first atom over here, we'll talk about it in terms. So if this is my first atom, I know that I have a nucleus and then I have electrons that orbit around a nucleus. Now, at some point in time, I may end up at having a distribution of, not an even distribution of electrons. I may have 2 electrons on this side and only 1 on this side, and so they don't balance out exactly, they don't cancel out. I might have an area of the atom that I have more electrons in, so there is a little bit of a negative charge that accumulates there because of the uneven distribution of the electrons around the nucleus. And if I have a little negative charge on this side, that will leave this, the opposite side of that, a little partially positive. We talked about these before when we talked about dipole formation. So it's kind of a review for right now. Now this can happen it can happen instantaneously in a system. And if I form this, what we call a temporary dipole, where I have just a partial negative charge on one side and a partial positive charge on one side, well, this is going to induce, we call induce, a dipole on a neighboring molecule, because now these electrons are going to push, right? We know that same charges repel, so they're going to push the electrons of this atom on the other side, opposite side from here, leaving a partial positive charge on the side closest to the delta minus here, and then a negative charge is going to form on the other side. Now these will go away as soon as they are formed, so they're they're temporary dipoles. And once that distribution changes, this dipole is gone. So once the electrons move around again in my nucleus, that dipole is gone and I still get a distribution of 0. And once the dipole is gone here, it's gone here as well, because I don't have anything to a charge here to push those electrons on the other side, so a negative charge to repel the negative charge, to leave me with a partial positive charge here. Once that temporary dipole is gone, in one molecule it will go in another, but it can come back as soon as it's gone. So you can see that at every instant I may have a part of the bulk. So if I have a bunch of these atoms or these molecules in a system, you can see that at any point in time I can have these mini dipoles going all over the place. And that is these little interactions then between temporary dipoles of one molecule and another, or one atom and another, being an attractive force. They can be, so if these two are opposite each other, it could be the repulsive force as well. But these types of interactions are what cause those dispersion forces, London dispersion forces. You can see that they're very weak. They're very weak because they're a temporary dipole. They do not stay around very long. So they're gone, they're here, then they're gone, then they're here, then they're gone, etc., etc. So they're very weak. Now they depend on the size and the shape of the molecule. So let's look at that. The larger before I go here, the larger the molecular weight or the atomic weight, the larger the London dispersion forces. So the heavier molecules will typically have larger dispersion forces because, well, think about it. If I go down a group, for example, and I'm just looking at the atoms right now, if I go down a group and I know that the the size of the atoms increases, I also know that I'm increasing the number of protons because I'm increasing, I'm going down a group, so I'm increasing the Z number. And because of that, I'm adding more electrons as well. And so I've got a lot more electrons around the nucleus if I have a larger atom. So you can see that electron density can shift around more electrons than a smaller atom. Also, it is easier to, we call this polarize, it's easier to polarize a larger atom, the electrons in a larger atom, because they're not held so tightly. Remember, the larger the atom, the more shells, electronic shells they're going to have around the nucleus. And those electrons that are farther in the outer shells, they're not held as tightly as those that are really close to the nucleus. So it's easier to influence those electrons as it is to influence the ones that are really close to the nucleus, because they're held so tightly by the nucleus. So we see that the larger the size of the molecule, the easier it is to form the dipoles, the temporary dipoles, and the larger the London dispersion forces. Now let's look at the shape of the molecule. That also makes a difference. So here's molecules that have the exact same molecular formula. They have the exact same number of carbons and the same exact number of hydrogens. They only differ in the way they connect to each other. The atoms connect to each other. Okay, so let's see. They're arranged. So here's neopentane, there's isopentane, and there's N-pentane. In this one, the carbons are arranged in just a chain. There's no groups that come off that chain. They're just right next to each other. So carbon, 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 carbon. They're all in a row. In here you have 4 carbons with one group of carbon being attached to one of the middle carbons here. So you have one side group is what we call these. And here you have 2 side groups. So you have a more compact molecule here and a more spread out molecule where this one is kind of in between. Now look at the boiling points. A boiling point is a way to measure the strength of an intermolecular force, and we will talk about it in detail when we talk about boiling point, but just real quickly right now, boiling point is a measure of how strong intermolecular forces are. The higher the boiling point, the higher the intermolecular forces will be. As we see here, neopentane, so these are arranged in order of increasing boiling point. Neopentane has the smallest, with N-pentane having the largest. Why is that? These have the same exact molecular weight, so that's not an issue, or it's not the determining factor. Now that I've crossed that out of the equation, I can look at the shape of the molecule. Well, if I look at this one, I have a small contact area because a lot of this molecule is so compact within each other that it doesn't have a lot of place that it can interact with another molecule. So it has a small contact area. Therefore, it will have the weakest attraction. This has a little higher than this but smaller than that, because it only has one side group, whereas this one has 2. And therefore, it has a little higher surface area than this. This less surface area is in comparison to this one, but it has a little higher surface area than this molecule. Therefore, it has more attraction than this molecule, but still not as much as this. Now here's this one. Look how long this is and how drawn out. I can interact along all of this surface on top, on the side, on the bottom. So the surface area is a lot more than these two molecules. And because all of my molecules the other molecules of N-pentane can interact with this molecule in all of this surface area, that increases the attraction between the molecules, which increases the London dispersion forces. And therefore, the boiling point is the highest of all these three. The first thing that you need to do then is to determine if the molecule has only London dispersion forces and nothing else. Then you can see if the molecules that you're comparing have different molecular weights. If one is heavier than the other, then that molecule will have the highest boiling point, or it will have the highest intermolecular forces, because the larger the size of the molecule, the larger the intermolecular forces. If they have the same or very, very close to each other, the molecular weight is very close, then you look at the shape of the molecule. And typically, because at this point we don't know how to connect all of these. If I gave you neopentane, you would not know what the shape of that molecule is. So for the shape of molecules, you would be given the structure this way. Then you can say the more compact a structure is, the smaller the London dispersion forces will be. The more spread out, meaning the larger contact area, the larger surface area, the higher the intermolecular forces will be. That is how you compare these two. Here's an example. Order the following compounds from lowest to highest intermolecular forces. Okay, so here's what I have over here. I have silicon tetrahydride, carbon tetrahydride, or methane, and then tin hydride, and germanium hydride. Now, for these, if you notice, all of these, so they'll have hydrogen, all have hydrogen. The only way they differ is from the first element. And if you look at all these four first elements, you'll see that they are in the same group in the periodic table. And because they are in the same group in the periodic table, you know that as you go down a group in the periodic table, the atom size increases. Therefore, the hydrogen is not going to it's not going to influence anything because they all have the same amount of hydrogens. So what's going to make a difference in the intermolecular forces for these four molecules is going to be the size of these atoms. And I know that as I go down a group, the size of the atom increases. So the first one for this in these four molecules is carbon. If you look at the periodic table and find where carbon is, you'll see that in that group, you will see that carbon is listed on top, is the first element. So because it has the smallest shape, or the smallest size, I'm sorry, not shape, then it will be the one that has the lowest intermolecular force because it has the smallest size. And then if you look in the periodic table, silicon is the next atom. So it is a little bigger than carbon, but not as big as these other two. So silicon will be next lowest. And then germanium will be it's next after silicon. So this germanium hydride will be the next molecule, and then the last one will be tin hydride, because tin is the largest out of these four. So here's the order in from lowest to highest. Carbon has the lowest, then silicon, then germanium, then tin, the lowest intermolecular forces, because carbon is first in the group, then comes silicon below it, then germanium, then tin. And as I go down a group, the size of the molecule increases, and therefore the intermolecular forces will increase. Now notice that all of these compounds, they have the same intermolecular forces. They only have London dispersion forces. That's why I can look at only the size of these atoms and nothing else. We will see other examples once we talk about other intermolecular forces, that we have to pay attention to the types of intermolecular forces as well. Okay, now let's look at this example over here. We have C3H8, C4H10, and C2H6. So this has two carbons and each bonded to three hydrogens. This has four carbons in a row, and this has three carbons in a row. As you can see, they're all three made of the same type of elements. So it's not going to be the size of the element that's going to make a difference, because all of them have carbon, all of them have hydrogen. But what's going to be the deciding factor here is the size of the molecule. How large, I have the same type of elements, but I only have two carbons here, three carbons here, and four carbons here. I have 6 hydrogens, 8 hydrogens, and 10 hydrogens. So as you can see, the molecular weight is increasing. This is the lowest, this is the next lowest, and this is the highest molecular weight. If you remember from the previous slide, that the larger the molecular weight and the size of the molecule, because I'm increasing the size, obviously, the size of the molecule, the highest the intermolecular force. So this is then the order of the intermolecular force from lowest to highest for this example. I have C2H6 as the lowest, and then right next to it is C3H8, and then lastly, with the highest intermolecular forces out of these three molecules, is C4H10, because they have the size is increasing and the molecular weight as well. Okay, let's talk about the next type of interaction or intermolecular force. It's a dipole-dipole interaction. These dipole-dipole interactions do not result from temporary dipoles. These result from permanent dipoles, from those molecules that are polar. They always have a separation of charge. It's permanent, therefore they're in between. Remember, we talked about covalent compounds and ionic compounds, and we talked about how in ionic compounds we have total separation of charge because we have total loss or gain of electrons. In a covalent compound, we could have nonpolar compounds, like we saw the temporary dipole type molecules, or we could have permanent dipoles, where because one element is more electronegative than the other, those electrons are attracted, that they share, are attracted more to one atom than the other, and therefore you have a permanent separation of charge, but not total, like in an ionic compound. It's a partial one. Those electrons spend more time around this one, but they still do a little bit over on this side as well. So it's not a total give or take of electrons. It's still sharing, but they spend more time on one side than they do on the other. That's why it gives that particular atom a partial negative charge, and the other atom has a partial positive charge. These are permanent dipoles. So if I have a lot of these molecules next to each other, then they're going to orient themselves in such a way that the negative end of one is going to be attracted to the positive end of another molecule, and so on and so forth. So you can see positive ends lined up all around here, negative ends lined up over here, etc., etc. They are present in polar systems, and they depend, so the strength of the dipole interaction depends on the magnitude of the dipole. How large is the dipole? You will figure this out by looking at the how polar a bond is. The more polar the bond, the magnitude of the dipole is larger. And the more polar bonds tend to have larger electronegativity difference. Remember, we talked about electronegativity values. The larger the difference in electronegativity, not the sum, but the difference, and you have a table with all of those electronegativity values in either the book or in the lecture notes, you can then find the electronegativity difference between two atoms of one molecule and then two atoms of another molecule that you're comparing. And whatever has the largest electronegativity difference, that will be the larger or the more polar bond. And if it is the more polar bond, then it will have a larger dipole magnitude, which will in turn translate into larger dipole interactions or larger intermolecular forces. Let's then look at some examples. Predict which will have the higher intermolecular force, N2 or CO. Okay, well, at first glance, I can see that this molecule is made up of the same type of atom, and this molecule is made up of two different atoms. So if I were to look at their Lewis-Dawes structures, I would see this is my Lewis-Dawes structure for nitrogen, and this is the Lewis-Dawes structure for carbon monoxide. This is the same type of atom. These are two different atoms. So if I were to look at the value for the electronegativity of nitrogen, these would have the same value, and so the electronegativity difference would be 0. So I would take the electronegativity value for this nitrogen minus the electronegativity value for this nitrogen. It's the same, would give me 0. Over here, the electronegativity difference is not 0 because I have carbon and I have oxygen, and these two atoms that make this molecule, they have different electronegativity values. Oxygen is more electronegative than carbon. So if I take the difference between these two, I will find that it will be more than 0. At this point, I'm not exactly sure what that would be, but you can do that to convince yourself. Because this has an electronegativity difference of, I guess, it's not 0, that makes it a polar molecule. This one is nonpolar because the electronegativity difference is 0. So between these two, because this is polar and this is nonpolar, this will have the higher intermolecular forces. Let's look at this example, ICl or Br2. Once again, let's look at their connection. ICl, here's the Lewis-Dawes structure, and here's the bromine. This molecule, just like the nitrogen, is made up of the same type of element, bromine. So if I did an electronegativity value over here, the difference, I would get a 0. Not here, this wouldn't be 0. And because this isn't 0, this is a polar molecule. This is nonpolar because it gives me an electronegativity difference of 0. Because this is polar, this will have the higher intermolecular forces. This molecule and this molecule, because they're nonpolar, they only have London dispersion forces and nothing else. These will have temporary dipoles only. Whereas these two molecules, because they are polar, they will have permanent dipoles, which means that they will have dipole-dipole interactions, which are stronger than the London dispersion forces, which are only only due to temporary dipoles. So for these types of molecules, now that we've added another interaction, the first thing that you need to do is determine whether what type of intermolecular force do you have? Do I have just London dispersion forces, or do I have dipole-dipole interactions? Dipole-dipole interactions win over the intermolecular or the London dispersion forces. So the first thing you need to do is determine the type of intermolecular force before you make a prediction on which one will have the highest intermolecular force. The next type of interaction, and the strongest that we're going to talk about, is called hydrogen bonding. This results from a really strong permanent dipole. It is a subset of dipole-dipole interactions. It's a special case of dipole-dipole interactions because it only occurs in specific types of molecules. It's found in groups of so in interactions that contain fluorine directly bonded to a hydrogen, oxygen that's directly bonded to a hydrogen, and a nitrogen that's directly bonded to a hydrogen. So in groups or in molecules that have FH, OH, or NH bonds and nowhere else. So this is where hydrogen bonding is. If you notice, these three molecules or these three atoms have very high electronegativity values. So the permanent dipole that they form is very strong. This is very important in biology because if you know anything about, if you've studied anything about biology, you'll know that the DNA molecule is held together by these hydrogen bonding interactions between NH and OH containing molecules. So interestingly enough, they're very important because in the DNA molecule, they're very important because the DNA molecule needs to break apart for the replication process, but it has to be so that the type of force that holds it together has to be strong enough that it doesn't break apart very easily. So these hydrogen bonding, the hydrogen bonding is important because it's a very strong force. It's not as strong as a covalent bond between an oxygen and a hydrogen of the same molecule, but it's in between a strong, basically a covalent bond and other intermolecular forces. So it is strong enough, but not as strong as a true covalent bond, because if it were covalently bonded, it would require a lot of energy to break those apart. Remember, the covalent bonding is the type of bonding. It's intramolecular bonds or molecular forces that occur between atoms within a molecule, whereas intermolecular bonding, like hydrogen bonding, occur between atoms of different molecules. And so here's my water molecule, and here's another, and here's another, and you can see that my oxygen, which if I were to do a Lewis-Dot structure, I would see that oxygen would have a partial negative charge and the hydrogens have a partial positive charge. So the water molecules arrange themselves in such a way that the oxygen is attracted to the hydrogen of a different molecule and a different molecule, or the hydrogen of one molecule is attracted to the oxygen of another molecule. So these interactions that are represented by dots here, they are hydrogen bonding forces. And they are the strongest that we're going to talk about. So out of the three that we've discussed so far, they are the strongest. Therefore, the first thing that you need to do as you compare intermolecular forces in different molecules is determine what type of bonding will each molecule have. If one of them has hydrogen bonding but the others don't, then that one will definitely have the highest intermolecular forces. Let's look at, well, before we look at an example, let's look at something interesting, how they figured out the part for hydrogen, the hydrogen bonding. Scientists were doing a study on boiling points, and remember we talked about the fact that as you have the same type of molecules, if I'm going down the periodic table, the intermolecular forces should increase because the size of the molecule increases. Okay, so we see here group 17, the halogens. We have HCl, HBr, HI. We can see that their boiling point is increasing, which is an indication of intermolecular forces increasing, which makes sense the way we talked about. Now, when they went to look at the HF boiling point, oops, that doesn't follow the trend. HF is much higher than even HI boiling point. And if you go to group 15, the next group, well, we see, okay, phosphorus has the boiling point that is lower than astatine, and there's lower than antimony. So arsenic, I'm sorry. So we have phosphorus here, arsenic, and then antimony. So they follow the trend of what you'd expect. This is the largest, and so this has the highest. However, when the NH3 ammonia boiling point was measured, you'll see that it's much higher than it should be. It should be down here. So it's a linear trend type. And then when we look at the group 16, where oxygen is found, and we see, okay, H2S, so here's sulfur, and then we have selenium over here that is larger than sulfur, so we have an increase in intermolecular forces, so increase in boiling point, and then tellurium is larger than all of these, so sulfur and selenium, so has a higher boiling point. This makes sense. But then when we look at water, look at how high the temperature of water is. So these anomalies led the scientists to figure out that there was something else going on with these molecules, a different type of bonding that increased the intermolecular forces so much to increase the boiling point. And this is why we see that for these three molecules, so these three types of bonds, so we have a molecule in water, we have oxygen that is bonded directly to two hydrogens, so it can hydrogen bond in two places. Fluorine can only hydrogen bond in one place because there's only one bond, HF bond. Now NH3 has three different bonds, but it's not as strong as water because oxygen is more electronegative than nitrogen is. So as you can see, it also makes a difference how many types of hydrogen bonding you can form. Oxygen or water here can make two, whereas HF can only make one. So even though fluorine is more electronegative than oxygen because it can only form hydrogen bonding at one spot, it has a lower boiling point than water. And then NH3, it can form hydrogen bonding at three different places because it has three NH bonds, but nitrogen is not as electronegative as oxygen. So water has a very high boiling point. Now let's look at a problem, or a couple of them. Consider the compounds dimethyl ether, here's the structure, ethanol, and propane. Their boiling points, they're not necessarily in order, are negative, so minus 42.1 C, minus 24.8 C, and 78.4 degrees Celsius. Match each compound with its boiling point and explain your reasoning. Okay, if you look at these types of molecule, you will have approximately the same molecular weight. So that cannot be it. The first thing that I need to do then is look at the type of intermolecular forces that there are there. Okay, I look at this one. I only have carbons and hydrogens. Therefore, this is a very, if there is any polarity associated with this molecule, is very, very small, because the difference between electronegativity values of carbon and hydrogen is very small. And so this will be very close to nonpolar. And we know that for those types of molecule, the only intermolecular force that they have is London dispersion forces. Because they only have London dispersion forces, they will have the lowest intermolecular force, which means that they will have the lowest boiling point. Okay, which is the lowest boiling point here? Minus 42.1 degrees Celsius. Okay. Next then, I have these two. This is CH3CH2OH. This is CH3OCH3. They have the exact same molecular formula, but they differ in the way that the atoms are connected. This is an ether, this is an alcohol. Now the way this is connected is this oxygen is in the middle of the two carbons. So the oxygen is bonded to this carbon and to this carbon, whereas here the oxygen is bonded to this carbon and to this hydrogen. As you can see, because this oxygen is bonded to the two carbons, I cannot form a hydrogen bond with this oxygen. The only way to do that is if the oxygen has at least one bond directly with a hydrogen. So in this molecule, I have hydrogen bonding because this oxygen is bonded to one carbon on one side, but it's bonded directly to the hydrogen over here. Whereas here, it's not the case. I have the oxygen bonded to the two carbons. And we know that oxygen only forms two bonds, so it's not bonded to any hydrogens. Therefore, we know that this has hydrogen bonding and this doesn't. So this will have the highest boiling point out of all three. So this will have 78.4, and this will have the next one, minus 24.8. So here's the boiling point for this one. And then the ethanol will have 78.4. And then lastly, propane will have the lowest boiling point because it has the lowest strength of intermolecular forces. Let's look at ethane. Ethane has a melting point of minus 183 degrees Celsius and a boiling point of minus 89 degrees Celsius. Predict the melting and boiling points for methylamine, which has this formula. Now let's look at these two individually. They have approximately, once again, approximately the same molecular weight. So that is not the determining factor here. What will determine the strength of the intermolecular force will be the type of intermolecular forces. As you see for ethane over here, once again, the same thing as the propane. These, the carbon and hydrogen have approximately the same electronegativity value, so the difference is very small. So this is, for all practical purposes, a nonpolar molecule. Because it's nonpolar, it has very low melting and boiling points. What about over here? I have the nitrogen is bonded to this carbon, and then nitrogen is bonded to two hydrogens. So if you look at the previous slide where we talked about the hydrogen bonding, one of the types of molecules that forms hydrogen bonding is one that has a nitrogen directly bonded to at least one hydrogen. And in this case, nitrogen is directly bonded to two hydrogens. So it can form two hydrogen bonds at those specific hydrogens. So the melting point and the boiling points for methylamine are going to be much higher than that for ethane because it has hydrogen bonding, whereas Ethane only has London dispersion forces. It doesn't even have a dipole-dipole interaction, permanent dipole. So let's look at the values for that. The melting point for methylamine is minus 93.1 Celsius compared to minus 183. So half of that of ethane. And here's the boiling point, much, much smaller, about minus 6 Celsius versus minus 89 Celsius. And that's because methylamine has hydrogen bonding, whereas ethane only has London dispersion forces and nothing else. This is the way you need to think about these types of problems. You need to determine what is the type of intermolecular force, the strength of the intermolecular force. If all of the molecules have the same type of intermolecular force, then you look at their molecular weight, which one is bigger, and if they have the same intermolecular, they have the same molecular weight, then you look at the shape of the molecule. Which one has the largest surface area? Which one has the smallest surface area? Etc., etc. Now, we also said that van der Waals forces are additive. So the more that are present, the more stable will be the compound, the condensed phase, which means it will result in higher melting and boiling temperatures. We already were doing these types of problems, but remember that they are additive. So if I have London dispersion forces and dipole-dipole interactions in one molecule, but only London dispersion forces in another, the one that has more van der Waals types of forces will have the higher melting and boiling temperature and the higher, obviously the higher intermolecular forces. So here's an example. I have here, it's a carbon, even though it's not, it's in both of these, and it's not written down. But if I look at these ones and determine which one will have the highest melting or boiling point, well, I look at first the type of intermolecular forces. Well, this molecule will have London dispersion forces. Yes, this will, because everyone has this. Now, because of the shape of the molecule, it's a tetrahedral molecule with all of the same type of atoms bonded to the central atom, then it doesn't have a dipole-dipole interaction because it doesn't have a dipole moment. It's a nonpolar molecule. So it has no dipole interaction and no hydrogen bonding because I don't have an oxygen or a fluorine or a nitrogen bonded to a hydrogen directly. No hydrogen bonding. So this molecule only has LDF forces. Now, if I replace these three chlorines with hydrogens over here, I'll say, okay, this molecule will have at least London dispersion forces because every molecule has at least London dispersion forces. Now, because I have a tetrahedral type of molecule, but I don't have the same type of element bonded to the main the central atom. Here I had all chlorines around the carbon. Here my carbon has one chlorine but has hydrogens on the other side. And because the electronegativity difference between the hydrogen and the chlorine is large enough, this molecule will have a dipole-dipole moment as well, a permanent dipole. So it has dipole-dipole interactions, but does not have hydrogen bonding because I don't have an oxygen or a nitrogen or a fluorine directly bonded to the hydrogen. So no hydrogen bonding, but it does have dipole-dipole interactions. Therefore, this molecule, because it has LDF and dipole-dipole, has higher intermolecular forces than this one, which only has LDF, which means that it will have a higher boiling point and a higher melting point. Okay, I will stop here for the first part of the lecture, and then we'll continue with viscosity and on.